So let's do an example for failure theories in brittle materials. Let's use our same bracket arm. And in this problem, the problem says that it's made of ASTM grade 30 cast iron. So therefore it's a brittle material. Because it's a brittle material, we know that your factor of safety has to be bigger or equal than 1. Remember, it's bigger or equal than 1. We know from tables your ultimate tensile would be 31 KSI and your ultimate compressive would be 109 KSI. That's very typical uh, for it's very typical for brittle materials itself. The problem doesn't state that, but we know that we should be using a design factor. In this problem, let's say 1.5. If it wasn't given, use 1.15. Uh, that's typical and is acceptable. So in this problem, this is the bracket. This is the part that we want to actually uh, work with. And you can see that here your small diameter is 1 inch. Your big diameter here is 1.5 inches. And this is your fillet radius, that's 0.125 inches. So you have this information, and we can find the tables to find the appropriate values. So R over D will be equal to 0.125. So that value is right here. And then D over big D is equal to 1.5. So is this value. So I just go up the here and come over here. So this is 1.6, about 1.75. So your KTA is equal to 1.75 in this problem. If you go to the next chart, this is again 0.125. Find 1.3. It should be very close there. So the value is somewhere over here. This is 1.2. This is 1.3. So you could say this is approximately equal to 1.38 maybe. This is your KTS. Then here, this is 0.125. You come up here, this is this curve, you're approximately here. So this value is a 1.6, 1.5 is over here. Maybe this is 1.56 approximately. So you can say your KTB will actually equal to this value. This is all eyeball, right? Approximations to this. We don't necessarily have the exact answer to that, but that's good enough for what we are doing. Okay, so from the problem or from the previous exercise, from the ductile material analysis, we know that these were all the results that we had. None of these values is actually going to change at all because we are still using it's the same beam, same loading condition, the same design factor. These are the loads. The only thing that's different now in this particular problem is that you can see that I need to multiply this by KTB and I need to multiply this by KTS. Okay, so these values are important, whereas in the previous case that was not so important. And from the previous exercise for the ductile material, it's the same problem. Nothing is changing. The only thing that we're going to change now are these two values that are important in the analysis. So to solve this problem, it's the same process that we did before. So we can build our status stress, and note that your status stress at point A will equal to sigma xx. This is 0. This is tau xz, tau xz, and this is 0, 0, 0, 0, and 0. And just remember from here, then we want to find the goal is sigma 1, sigma 2, and sigma 3. This is what your failure theories are going to require for these problems. And then we're going to use our MATLAB code to actually solve this as we did in the previous example. So let's go ahead and run the MATLAB code. Again, it's the failure theory. So we are running this, and to run it, I press run. I change the folder if it's not in that folder. You need to work in the working directory. So we are working in inches. This is KSI. The problem says this is 1.5. I know the loads here. Like I told you, let's go ahead and ignore the values for F. Just ignore F, put the coefficients of F. We will add F at the end. So your moment was 15. Your moment was 15F. So we can just write 15. Your bending moment was minus 14F. We can write minus 14. This was minus 1F. So we can write 1. And now we're going to say number 2 because brittle material is going to ask for ultimate. And the value for ultimate, the values were, just give me a sec. The values were 31 and 109. So 31, 109. Stress concentration factor for the axial load. We are not using it, but for completion, can come here. It was 1.75. So the axial load stress concentration is 1.75. Your bending stress concentration, your bending stress concentration factor is 1.56. So you can write that value there, 1.56. This was 1.38 for torsion. Then you run this. After you're done running it, just give it a moment. So now you have a file that's called Brittle TX. You see it? This is the file we will open. And if you want to see what the plots look like, you can open plot. This is the plot. And this is what the plots actually look like for this problem. You can see that, don't worry about this. This is really not representative of your problem because we didn't give a value of F, okay? But we multiply by F and this is going to be taken care of. So in reality, what we are trying to say is in this particular problem, your loading sequences this is the load line, and that's your load line, and it's safe somewhere, anywhere here. And the theory that we typically use is the modified more, so it's this one right here, not so much this one. In this line, in this quadrant, we can see that they actually coalesce each other. So that's what the plot tells me. But let's see what the results tell me. So when I run this, it does the whole analysis and says, this is my state of stress. You see these values? So these values will give me what my stress really looks like. So it says that your state of stress for this problem, after you do the whole plug and chug of everything, will be 333.7 F, 158.1 F, 1.581 F. Okay, don't forget the F. The F is there. And this is given in KSI, so I'm changing that to PSI. That's why you have those values. So your state of stress, these are your principal stresses right here. So the principal stresses in your problem are given by, your principal stresses are sigma 1, it says is 0.397 KSI, but we're going to convert that to 397, and I'm going to add the F that was missing, and that will be PSI. Sigma 2 is 0. Sigma 3 from my code, I find this is minus 0.063. So that gives you minus 63. This is this is KSI. And now I'm going to say this is equal to times F PSI. Remember, I eliminated the F. Now I can put the F back into my problem. I really don't care for shear. So the first check I do is a simple tensile and compressive check that always needs to be done, but don't have to do in this problem. The first one is normal normal stress criterion. In the normal stress criterion, we can see that you have a factor of safety of 78. So how do you interpret that? The interpretation of that is, so for the first case, maximum normal stress theory. So the problem actually is telling you the case that it's working with. This is the ratio, and you can see, and if the ratio, this ratio is 30, this ratio is 3.5, and this ratio is 0.59, and so we are saying that this ratio is actually bigger. Okay, so that's the case that we will be using. Small correction here, this should be less or equal than 0, less than equal than this ratio. So this is 3.50, 3.5. 3.5 is bigger than this, so this is the case that we are using here, okay? And you can see that it makes sense because we are, because of the plot, you are actually in the negative direction, right? This is S3, so you're really is negative. That makes sense. So you come here and then you can say, so basically what you're doing here is, in your problem, you're saying that your factor, your safety factor is equal to 78.086. It has to be divided by F, has to be bigger or equal than 1, as we did before. And then from here, F has to be less or equal than 78 pounds. Okay? The second case that we are working with is the modified more. This is using your diagram from your book, and actually I should get a very close answer, and it's expected. So it's the same thing. You do these two ratios and choose which one actually satisfies the case, and you can see that's actually equal to 7806. Gives you the same value. Now you could have also used the modified more using these equations here. which is what we really recommend that you always use. By using that, you're going to see you get exactly the same value as well. Brittle column more is a bit different. You can see that it's going to be the most conservative case. It's going to be the smallest value. All these three others will give you, in that particular region, should give you the same, because we are actually in the same on the same plot. Okay, these two cases here are same. They're different using different equations. This is a lot easier to use actually. So if I was going to do the last one for the column more, just to show you column more problem. And then you say here, this you have the factor safety here gives you 74.7 divided by f has to be bigger or equal than 1. And that would give you actually f has to be less or equal than 74.7 pounds. Just as a review, why this is at the bottom, because remember, we had strength at top, okay? And then at bottom, the equation that we used was sigma 3 at bottom. And sigma 3 is what's multiplied by F, okay? This is what's multiplied by F. So therefore, that's why it's at the bottom, okay? Because my code just gives me the ratio, gives me this whole ratio, and I didn't include the F in my analysis. So this is one part of the problem. The second part of the problem says, what happens is F is equal to 80 pounds and F is equal to 75 pounds. So we actually, all we have to do is go back to these equations, and you can see that for my both cases, right? So we could make a small table here. We could give values of F, and we could say the maximum normal stress theory, and we could do a modified more. That actually gives you the same value. We could do column more. And this told you the F has to be less or equal than 78. This said that F has to be less or equal than 78 as well. This one said the F has to be less or equal than this value. So the first load that they're asking is 80. So if this is 80, this definitely is above this value, so this failed. It's a failing point. The structure also failed here, also fails here. Okay, these are all failing. The next point load that they give you is 75 pounds. So if I add 75 pounds now, you can see that for maximum normal stress theory, this is safe. This one is also safe. This is the one that we really care for. This one right here, we really don't care for this one. And this one just say slightly, it just fails. But remember, this is the most conservative one. It's going to be always the most conservative one. So it's going to actually beef up your structure. And it always has the tendency of beefing it up. So if you're going to solve this problem iteratively, let's suppose we want to find a dimension D or any other dimension, then basically the whole problem reduces to, again, as I told you previously, give different values of D, okay? So basically the whole idea is the following. Prepare a table and say, what happens with D? What is my factor of safety? And then what happens? What happens if I start with D is equal to 1? Then maybe your factor of safety is 0.9. Oh, then I have to go up. Then maybe you put 1.5, and now the factor of safety became 1.7. Oh, wait, I need to go down because I want to bring this factor of safety as close to 1 as possible. then I keep iterating, okay? I keep putting different values for this until I can somehow reach this. But these are hypothetical values, by the way, completely hypothetical. And until I can reach a value in which my margin, my factor safety is actually equal to 1. Okay, so this concludes the discussion on uh, brittle fracture failure that actually includes stress concentrations.